Hi there. I thought I would tape a video today on what we did in class, just in case we're not here tomorrow. So the first thing that I wanted to talk about was just kind of go over what the formulas were that we used in case you missed class today or didn't get them down. So we are talking about segments of a circle this time, and I'm on page 25 of your packet. So segments of a circle are different than arcs and arc measures and angle measures. Segments actually have to deal with the length of the segments. And so we have 4 different types of segments we're going to talk about. The first type of segment is a chord, and a chord is always going to be part times part. And you'll understand this when we get to seeing what a chord is. So, well, I'll just go ahead and show you. So part of a chord, it would be AE times EB, times the other part. And I'm talking about of the same chord. So the next type of segment that I'm talking about is a secant. And here, a secant, whenever I'm dealing with that, I'm going to deal with the outside length, the length of the outside part of the secant, times the length of the whole secant. And so what I'm talking about here, if you turn the page, you will see secants here. And I'm talking about EA being the outside part and EB being the whole. And we'll go back and look at that. The next one is a tangent. Okay, and a tangent is one that hits the circle only one time. And so a tangent is actually going to be tangent squared, because seeing that it only hits it one time, there's nothing else to multiply it by. And so what I'm talking about there is this one. EA is a tangent here, or I have tangents there. So going back to what else we also have a radius, okay? We also have a radius, and when I have a radius and a tangent, they form a right angle. So those are the 4 different types of segments I'm going to see. And when I see the diameter, I'm going to treat that exactly like a chord. So moving on along, going back up here, you can see these are pictures and examples of each different kind. And here's the theorem that goes along with it. Now this is a little bit harder to prove, so we're just going to talk about the theorems and go through it. So it says the product, because I'm always multiplying, of the lengths of the segments of one chord is equal to the product of the lengths of the other chord. So what that means is, because I have 2 chords, if you recall from down below, part times part is equal to part times part of the other chord. Okay, meaning AE, so the length of AE times the length of EB is equal to the length of DC or DE times the length of EC. Moving on down to the next one, you can see this one, I have a radius and a tangent, and we talked about it earlier. It always, when a radius and a tangent meet at the point of tangency, it's always a right triangle, and so anytime I think of the right triangle, I think of the Pythagorean theorem. So I can use a squared plus b squared is equal to c squared and other right triangle properties to solve for the missing piece. So in this case, you need to know that going from the center to the end of the tangent, not the point of tangency, it is 3 squared plus 4 squared is equal to 5 squared, and it actually works, so it is a right triangle because 25 is equal to 25. So moving on along and turning the page to page 26, we have 2 secants, and if you recall from earlier, it's outside times whole is equal to outside times whole, because there's 2 secants. Outside times whole for the top secant, and then outside times is equal to the outside times the old whole for the bottom secant. So it says the product of the lengths of the external portion and the whole secant equals the product of the lengths of the external portion and the whole secant of the other. So this probably is one of the most difficult ones because you have to remember to add to get the length of ED. So you have to add the length of EC to the length of CD to get the total length ED. So what this means in terms of this particular circle is the outside length, which is EA, times the whole length of that secant, which is EB, is equal to the outside length of the other secant, EC, times ED. In the next video, we'll actually go through and solve some using these formulas. So the next situation gives me a special situation where I have two tangent lines and they're connected with the radius, and the tangents end up being equal to each other. And the reason that is because I have the first tangent squared is equal to the second tangent squared. And then I can take the square root of both sides, and so the tangent is equal to the tangent length. And then the last formula, and really you don't have to memorize all these formulas, you just have to know if it's a chord, it's part times part. If it's a secant, it's outside times whole. If it's a tangent, it's tangent squared. A radius and a tangent make a right angle. So there's 4 things you need to remember. So this one consists of a tangent. So EA, I have tangent squared, and a secant, so I'm going to set that equal to outside times the whole. Okay, and so in this particular case, I have EA squared is equal to EC times ED. And don't forget, sometimes to find ED, you have to add EC plus CD. So the product of the lengths of the outside segment and its whole segment equals the square of the length of the tangent segment. So my next video, I will go and try to do some problems for you.